All right, welcome to section 2.1, tangent and velocity problems. So in chapter 2, now we're going to start on something called limits. And this is a huge part of calculus. You're definitely going to want to make sure you're strong in this chapter so that you do well in all the rest of the chapters and the rest of your calculus courses from this point on. All right, so the tangent problem. So if you remember way back in your geometry days, you heard that term tangent, right? So tangent, what we're used to say, the definition we're used to from geometry is, it's a line that touches a curve in exactly one spot. But a little further than that, right? We actually make it touch the outer part, right? In other words, kind of glance off the curve, not really cross through the curve, okay? All right, so the word tangent is derived from the Latin word tangens, which means touching. Now that makes sense. Again, we just said, that line's going to touch the curve in one spot. Thus, a tangent to a curve is a line that touches the curve. In other words, a tangent line should have the same direction as the curve at the point of contact. For a circle, we could simply follow Euclid and say that a tangent is a line that intersects the circle once and only once, as in the figure below. For more complicated curves, this gets to be a little messy, this definition here. So what we're going to look at is this figure here. Okay. The figure shows two lines L and T, right? So here's T, here's L. So the blue line is L, pink line is T. They're passing through a point P on curve C. So the line L intersects C only once, but again, like we talked about a minute ago, usually when we think of a tangent, we think of it glancing off the curve, not crossing through. Line T, so right here, line T, the pink line, looks like what we think of as a tangent line. It glances off the curve C, but the problem is, well, over here it hits it again, right? It hits curve C again. So kind of a little issue here on the definition of tangent. All right, so what we're going to look at here is definition, so we're going to, an example, so we're going to find an equation of the tangent line to the parabola y equals x squared at point P, 1, 1. So that's right here. That's my pencil. There we go. Right there. That's what we're looking at, point P, 1, 1. All right. So here's the solution. So basically, you can read through this solution, but what I'm going to talk about here is this graph, right? To find the equation of a line, we need a point and a slope at least, right? Or just 2 points. With the 2 points, we could find the slope, excuse me, and have that other point available. Either way, those are the things we need. The problem is P, or the point P, 1, 1 is a single point, right? So with only that information and it's kind of hard to find the equation of that tangent line if we don't have a second point on that tangent line. So what we could do is we could pick another point, right? Let's say this point right here, Q, x comma x squared. It's somewhere on the curve. But if we use that point right there to approximate t, to approximate the slope and equation of t, you can see as the blue line connects those 2 points, that's a problem. That's really far off, really, from line t. So it would not be a good approximation, right? So what we could do is we could bring Q a little closer down the curve, but still, we're going to be off, right? That the line between P and this pink dot right here that I drew in is still not going to be exactly the same slope and equation as line T, that tangent that we're trying to figure out. Well, we could just keep bringing that point closer and closer and closer to P every time on the black curve, on the x squared curve. But the issue is we're still going to be off every time, right? We're still not getting too great of an approximation of the slope and equation of the tangent line T. So this is the basic concept of limits. Limits are going to tell us, let's bring that point. So, I keep bringing this point closer and closer and closer to P. Well, what if we bring it infinitely close to P? Infinitely close. So close you're not going to see a difference, right? Now with a point infinitely close to P on the curve, still on the x squared curve, then when we use those 2 points, we can find the slope, which means we can find the equation of the line. And since it's infinite, since that extra point we got was infinitely close to P, the difference between the slope and the intercept of this new line we're trying to find and the tangent line are so small that it doesn't matter anymore. Okay, I hope that makes sense, but that's the basic concept that we're trying to do here. Okay, all right, so that's the important part there. Let's see. So we choose, or let's go up to the top here. So solution, we'll be able to find an equation of the tangent line t as soon as we know its slope, right? That's why we said we needed that second point to find slope. The difficulty is that we know only 1 point P on T, whereas we need 2 points to find the slope. But observe that we can compute an approximation to M, your slope, by choosing a nearby point. That's what I was just talking about, that point Q that we kept bringing closer and closer and eventually infinitely close to P on the parabola, and computing the slope, MPQ. So this term right here, this notation M sub PQ, it just means the slope between points P and Q of this secant line PQ. Remember, secant line crosses a curve twice or more. A secant line, from the Latin word secans, means cutting, right? So it's a line that cuts, intersects a curve more than once. So let's choose some x value that is not equal to 1, right? Because point P has an x value equal to 1. We don't want to choose the same point. So that point Q and point P are not the same. All right. So then the slope between P and Q is x squared minus 1 over x minus 1. All right. For instance, for the point Q 1.5, 2.25, so we'll say, so here's x equals 1. We're going to pick, again, something close. We're going to pick 1.5 and see what that slope is, right? So that's easy enough. We could calculate that. So if we plug that in, that's going to be 2.25 minus 1, right? Because we're using P and Q, over 1.5 minus 1. And if you calculate all that out, let's see, what do we get? 1.25 over 0.5, which is 2.5. So there's the slope between points P and Q. Okay, but again, like we said, 0.5 away on the x-axis is actually quite a bit far, right? So our approximation of the slope is actually going to be quite a bit off, relatively speaking, of course. So what we're going to do, so I accidentally copied this chart twice. Ignore that second one there. So what we're going to keep doing is, well, let's see. Let me start again here. So we're going to pick a point close to P, right, called point Q. But we're going to start with an x value of 2. If we plug that into the slope equation with point P, we get a slope of 3. As we just did, we'll move a little closer on the x-axis to the point, or to point P, plug into the formula. Now we get a slope of 2.5. But 1.5 is still pretty far from that x value of 1, so let's get even closer at 1.1. And then keep going closer at 1.01. And then even closer, 1.001. And look what's happening to our slope values. Right? We can see as we get closer and closer and eventually infinitely close to x equals 1, which is where point P is, right? Point P is 1, 1. Then our slope looks like it's rapidly approaching the value of 2. And at some point you can tell, right? You can already see the pattern. If we do 3 zeros in there, it'd be, if we do 3 zeros here, it'd be 3 zeros here. 100 zeros here would be 100 zeros here. Okay, so again, like I said before, since we're getting so infinitely close to point P with this new point Q, the difference is not going to make any difference in the slope. It'll be a good approximation. Okay, so that's the basic concept of limits. All right, we're going to keep bringing that point closer and closer and closer and infinitely close to point P to find that the slope of the tangent line, so that the difference no longer matters. Okay. So we say, there we go. We say that the slope of the tangent line is the limit of the slopes of the secant lines. In other words, like I was saying, is the difference no longer matters. We express this symbolically by writing right here. So this is important stuff. Oops. This is important stuff. Notation. Okay. The limit. So we say right here. What is wrong with this? There we go. We say the limit as Q approaches P. In other words, as we get that point Q infinitely close to P, the slope between P and Q equals M. M is the slope of our tangent line. Okay, this is more proper notation here. So this right here, the statement is the limit as x approaches 1 of this function equals 2. Okay, so one more time. The limit as x approaches 1, so that's as we're sliding x infinitely close to 1 of that particular function right there equals 2. Okay. Assuming that the slope of the tangent line is indeed 2, we use the point slope form of the line, the equation of the line, plug everything in, we get our equation for our tangent line, and that'll be 2x minus 1. Okay. Now all these graphs right here are just showing what I was talking about. We don't always have to come in from the right? In other words, let's follow these top 3 graphs. So we're looking at these top 3 graphs right here. And notice what's happening to point Q, right? Point Q is way out here. Now it's getting closer to P. Now it's even closer to P. And like we said, when we do limits, we're going to bring that point Q infinitely close to point P. On the bottom, we're just going to approach point P from the other direction, from the left. So here's point Q. You can see that one. That blue line is definitely not a good approximation for the pink line, the pink tangent line. But we'll keep bringing Q in closer from the left and even closer from the left. And again, as we bring it infinitely close to P from the left, we'll get a very, very good approximation of the actual slope of the tangent line. Okay, so that's important stuff to understand. All right, so let's see. We have this velocity problem right here. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 10 seconds, or after 5 seconds. Okay. Here's the solution. So through experiments carried out 4 centuries ago, Galileo discovered that the distance fallen by any free-falling body is proportional to the square of the time that it has been fallen. This model for free fall neglects air resistance. So you guys have heard of Galileo before, right? Famous astronomer, physicist, mathematician. He's even in that song, isn't he? Yeah, you've heard it. If the distance fallen after t seconds is denoted by s of t, so s, so if you're familiar with physics, s is the position function, s of t, position versus time, and measured in meters, then Galileo's law is expressed by the equation s of t equals 4.9 t squared. The difficulty in finding the velocity after 5 seconds is that we're dealing with a single instant of time at time equals 5. So the way this ties into what we were just talking about with the limits is if we go back up here, the problem is we only had 1 point given to us on that tangent line. So what we did was we brought that second point Q infinitely close, got our second point, and then we were able to calculate the slope. That's very much the same thing we're going to do here. We're going to pick times closer and closer and closer to 5 seconds, and then eventually infinitely close to 5 seconds, so that the difference no longer matters. Okay? All right, so like I said, so no time interval is involved here. There's one single time, but we want the slope. However, we can approximate the desired quantity by computing the average velocity over the brief interval of 1/10 of a second, right? So again, we're bringing those times infinitely close together, starting with 5.1 seconds. So if we do that, we'll plug in here, okay? So average velocity is change in position over time elapsed, right? So from 5 to 5.1 seconds, there's 0.1 seconds has elapsed, right? Change in position, well, we're just going to plug into the position function and calculate here. So let's see. So S of 5.1 is 4.9 times 5.1 squared. S of 5 is 4.9 minus 5 squared. I'm sorry, 4.9 times 5 squared over that time elapsed of 0.1. Plug and chug, all right? You'll see you're going to get something like 49.49. Okay? And there's your slope, right? There's your average velocity, same thing. But again, 0.1 seconds in the grand scheme of things, especially when you're talking about physics and physics applications and calculations, 0.1 seconds is kind of infinite, right? It's huge. That's a big gap, right? So let's, as we did before, let's start bringing this gap closer and closer. So first we'll look at 1 whole second here. And we see the average velocity is 53.9 seconds, right? But again, in 1 second, a lot can change. So what we just looked at was making the interval 0.1 seconds. And we got that slope of 49.49. Let's make that interval even smaller. So 0.05 seconds. Even smaller, 0.01 seconds. Even smaller still, 0.001 seconds. And we can see by the pattern here, our average velocity is really getting really close to 49 meters per second. Because again, we can see the pattern. If we have 100 zeros here, we're going to have 100 zeros here as well. Okay? So as we shrink that time interval, as we bring the second time infinitely close to the first time, we're going to get a very good approximation to our average velocity. Okay? It appears that as we shorten the time period, the average velocity becomes closer and closer to 49 meters per second. The instantaneous velocity when t equals 5 is defined to be the limiting value of these average velocities over shorter and shorter time periods that start at time equals 5. That's what we were just doing. Thus it appears the instantaneous velocity after 5 seconds is 49 meters per second. Okay? So here's the main idea. Even though we only know that one point, like in the first graph we did today, and also in the problem we just did, where there's only one instance of time, but still want to find the equation of a line, we're generalizing the line by finding the slopes of the secant line just to the left and just to the right of the tangent line itself. Remember, the tangent line is what we're trying to get the equation for, the slope and the intercept for. Okay? So, and this is something you'll see come up later. All right, so the slope between P and Q, in other words, the slope, in this case, the instantaneous velocity between 5 seconds and something really close, can be expressed with this equation here. All right, so we'll have some time. So in the case we just did, time was 5, right? So A would be equal to 5 in the problem we just had. Oops, A equals 5. And then H, well, we'll see later. We're going to end up, once we understand limits, we'll be able to easier do problems like this. But in the grand scheme of things, what we're saying is we're going to look at the position function evaluated at a plus h amount of time minus the position function at the specific time a over this small difference. Okay? All right, so for now, that's the lecture. Take my word for it. Now, on this lecture, just understand the basic concepts of what I'm talking about, okay? The whole point here, the big picture we just talked about in this chapter, is bringing those 2 points infinitely close together so that we're able to have 2 points, so that we're able to calculate the slope and get a really good approximation for the slope of our tangent line. Okay? Thank you.